so the next one we are looking at. Okay, yeah, this is a good one. So we'll do. Right, here's the next problem. We have 3-point charges are located at the corner of an equilateral triangle. Now calculate the electrical field at a point P located midway between two charges on the x-axis. All right, we'll see what that means. And if a, yeah, let's just figure out the A first. So can you kind of draw what that looks like? So probably maybe fit one of the lines on the x-axis, just because they said calculate the electric field at point P located midway between two charges on the x-axis. Yeah, just make one of the bottom flat, right? Yep, that diagram looks good to me. Yeah. No, it's okay. You didn't really need to even put the axis in. You just need to, yeah. Yep, so I want point P located midway through the two charges. Alright, so I'm gonna give you, yeah, so I'm gonna give you, did they say different charges or same charges? Calculate, 3-point charges. Yeah, I need to give you, the coulombs. So this is gonna be 3 nanocoulombs. This one's going to be 8 nanocoulomb, and they're all positive. And then this one's going to be 5 nanocoulombs. Yeah, kind of important information there. But you know the distance, I'll give it to you as well. It'll be 0.5 meters. So equilateral means all of them are going to be the same. Okay. So go off that. So I basically need, so I would begin by drawing a vector. Yeah. Yeah, exactly. Acting. Yep. Yep. Yeah, so see, drawing that saves us time, right? Because if we see any equal and opposite ones, we can just cancel them out. Actually, no, never mind. The bottom two are not the same charges. Never mind. Yeah. So if they were the same charge, we can cancel them right away. But yeah. Okay. Yep. Yep. Setting right as positive. Yeah, because then, yeah, E1 would be 0.25, right? Distance wise. Because if the whole thing is 0.5, then the distance to from P to test charge number 1, I guess. For half. No, yeah. The whole thing is 0.5. Yep. Yep. So that's the vertical distance to 3. Right? Yep, exactly. So just the two components, the horizontal and the vertical, you can add them up and then put them back together at the end. Just gonna zoom out a tiny bit. Alright, let me just see that. Let me find where was that question? Yeah. Okay. I was looking for the next problem already. Yeah. I'm just checking. I went back. Okay. It is. One. Oh. A force of 1 point. I got 1.88 times 10 to the 3 newtons per coulomb. So let me see. You got first of all, you drew them wrong a bit. So remember, these are positive charges, right? If you have positive charge, positive charge, positive charge, yes, this would push it this way. So you probably got the left and right mixed up, and then the up and down mixed up, because a positive at the P would actually get pushed down, right? Mm-hmm. Yeah, but magnitude-wise should be the same though. So let's see what else might be wrong. Ah, so no, not wrong. So basically, yeah. So the only thing you did was what was that? You didn't. No. Yeah. Because I gave you a different magnitude. For the bottom right one, they wanted -5. And I wrote +5. So that's my bad. But it's okay because because the calculation wise is correct. Yeah. So magnitude will be the same for what you get. So given your numbers, yeah. Well, not just down, because I feel like you probably got the left and right mixed up too. Yeah, because then the 1150 is probably the one going to the right. Because 1150 is this one, and 719 is this one. Yeah, so it should be right, left. Yeah, yeah, so just switch up the east. I would actually argue it would be east 18 south. If you think about, you got your first answer was west 18 north, then it should just go in the opposite direction, right? Since you just mixed up the left and right and up and down, right? Then it should just go in the exact opposite direction. In that case, it should be east 18 degrees towards the south. So that's your vector. Yep, and that number should be right. Okay. Let's see if we have time to get finish this one. Yeah. I'll just give it to you. I'll just give it to you, and you can maybe finish it or you can figure it out. So, yeah. Oh, Pepe's already on there, I guess. Okay, I'll paste it down here. So if a charge 1 nanocoulomb is placed at P, determine the force acting on this particle. Actually, no, it shouldn't take too long, because we already found out it's the electrical field, right? What's the relationship between the electrical force and electrical field? Yeah. Yeah, it's just Q, right? Because it's just Q times E, really, right? Because E is just a version of F without one of the test charge, right? Yeah. Yeah. Times. Exactly. -9. Nanometer. Nano coulomb. Oh, you already yeah. Okay, yeah. You got. I thought you wrote out the original. So yeah, I thought you wrote the 454. Yeah. Okay. Yeah. So that's right. Yeah, and then yeah, the direction would be the same. And what's the unit for this guy? Exactly. Yeah. There you go. Yeah. How about I'll find some and I'll send it to you over the next 2 hours. Okay. Okay. All right. So I'll see you the same. Maybe I'll text you if we're going back to 11 to 1 or 1 to 3. Is that okay? Okay. I'll text you sometime this week. All right. See ya. No problem. Bye. All right, for those of you watching the stream, I am just gonna quickly get on with the next student. But as you can see, I've muted the student. So if you're studying, you can study with me. If you got questions to ask, you can throw them on there. I'll try to sneak in the answer somehow during the session. But of course, please relate it to the subject that I am talking about. Alright, let me get my next student on real quick. Copy. Alright, so the next one should be a grade 12 chemistry. But sometimes she has math questions too, so we'll see. But definitely it will be in the grade 12. So today, mostly focusing on grade 12s. And yeah, we will see. Let me switch over the board to the next students. So you can see there's right now I have 23 students that are using this board with me. Who are all taking online lessons with me at the moment. So the university kids are dying down, so I got a little bit more free time now. Hey, how's it going? Oh, wow. You look like you just woke up. Okay. Okay. No, it's your hairstyle. It's it's a bit pineapple-y. It's all good. That's good. Okay. All right. All right. Next. What are we working on today? Oh, right. Okay. Let's give you the Zyboy link. Invite right here. So what time have you been sleeping now? You've been shifting to like 6 a.m. No, you have to be sleeping at like 6. So what time did you sleep last night? Oh wow, yeah. That's not bad. Okay, is this test coming up? Are you planning to write this test anytime soon, or what's the plan here? Okay. Okay, so you want to screen share anything you want me to see, or do you have specific questions today, or did you want me to continue talking about? I did, yeah, on the chat. Oh, I did you want it on your text? I will send that over on your text. There. Now you have it on your text as well as the Zoom chat. Okay. Specific impact on the equilibrium of, can you remind me of your oxygen? Right. So okay, so let's see what that equation even is first of all. So we're talking about oxygen as a gas, right? You breathe it into your lungs, and we are combining that. Well, some of it can combine with water, but that's very minimal. We're combining with the hemoglobin. Let's just write HB for now. Hemoglobin. Okay, and then so that will have an equilibrium between the O2 binding to it and of course back to it being unbound. So right here we have the O2 bounded to the HB. So we're saying, what does high altitude have on this equilibrium? Is it going to shift to the left? Is it going to shift to the right? Or is it going to not affect it? And this, I should write something maybe like an AQ or something. All right. So higher altitude means less pressure, right? Less pressure. that's one of the effects we wrote earlier. We have different Le Chatelier principle effects. One of the effect was on the volume and pressure. That one affects gas, right? The more volume you have, if you increase volume, you're going to shift towards the side that has more gases so you can expand into it. Okay? But right now we're not talking about volume, we're talking about pressure. We're talking about lowering pressure. Lowering of pressure is the same thing as shrinking the volume or expanding volume, you think? Because I always think in terms of volume. Because volume is easier, right? Because if you have bigger volume, you need to expand gases to fill it. If you have less volume, you want to contract, or you want the side with less gases. So if you decrease pressure, is that same thing as increasing volume or decreasing volume? You can think of, yeah, if you don't remember, you can decreasing volume. So pressure and volume go in opposite direction according to this equation, because holding nRT the same, as P increase, volume will decrease. As volume increase, pressure will decrease. The way to think about that is, if you increase pressure, squeeze onto something, well, the volume is gonna be lowered, right? If you release that tension, if you don't squeeze on it as hard, well, you're gonna let the volume expand, right? That's the real world way of thinking about it, I guess. So decreasing pressure has the same effect as increasing volume. So there we can reason it out. If you increase volume, do you want to go on the side of the equilibrium with more gases so we can fill it, or do we want to go to the side of the equilibrium with less gas? You want the side with more gas because you're increasing volume, so you want to go fill it, right? Yeah, I know. I am talking about pressure, but pressure is harder to remember that rule by, right? Volume is probably easier to remember. I mean, you can remember it from pressure as well. If you squeeze down on something, pressure, you have less room. Well, actually, that's still relating to volume. But you will have, these gases have less space, to kind of move around. So you kind of want to move into the equilibrium side with less gases. So that's why if you look at this equation, which side has more gas? Because right now we're trying to move to the side with more gas. So on the left side I have a gas and an aqueous, and then on the right side I have an aqueous. So the left side will have more gases. So therefore I am shifting my equilibrium towards the left. Does that kind of make sense? Yep. So that's one explanation. I mean, that's definitely one explanation. So if we go in high altitude, the higher up we go, right, the less pressure there is all around us. You can almost think about it like no, I don't want to talk about it from the biological perspective because this is chemistry. I don't want to, unless okay, yeah. Right. Okay. How equilibrium is impact. Okay, so I guess I can talk about it in terms of biological perspective as well. So from the chemistry perspective, this is it. That was the explanation. With the equation with the Le Chatelier principle, right? We have less pressure. Same thing as saying there's more volume now. So we want to go to the side with more gases, right? To fill in that volume. Now we can talk about from the biological, and I think you'll like that explanation a little bit better because, biology is always, I guess, a little bit more concrete and it's a little bit less abstract. That's not what they're talking about then. No, because what's the impact in the biological sense is that you're going to have less dissolved oxygen. You're going to have less oxygen distributing to the rest of your muscles. Muscle fatigue is going to be quicker. you know, maybe your brain uses up 20% of your oxygen, so at some point, if you're lacking oxygen in your head, then you're not going to be able to think properly, and that's why part of the high altitude sickness is, you know, maybe hallucinations even, getting to really severe cases. All right, but I do want to kind of touch up on the biological sense. So, because you've talked about biology in the respiratory system last year, right? So, in order for you to inhale something, right, we're making negative pressure in our lungs. Okay? So, negative pressure in our lungs, and how do we kind of create that? We expand volume, right? That's why we open up our intercostal muscles, right? We lower our diaphragm, so then we have more volume in our lung cavity. What that allows us to do is expand our lungs and create a negative pressure in there. What does negative pressure mean? You're going to have the air flowing in. Okay, so remember that. So the difference in pressure, the delta P, the difference in the atmospheric pressure, which is the outside pressure, the air pressure, and your lung pressure, that's going to determine how much air fills into your lungs, right? So here, if we're saying the higher up altitude there is, the lower the atmospheric pressure, keeping lung pressure the same, then your delta P is not going to be as big anymore, right? So decreasing P atmospheric pressure is going to lead into difference in delta P, because you can only create so much negative pressure in your lungs, right? You can only expand so much. So that's not really affected by the high altitude thing, right? Unless, you know, you talk about your muscles isn't being able to work as hard, then that's even worse. Then that will make this even less of a delta P, because you're not able to create such a negative pressure in there, right? But anyways, but if we forget that, let's just keep it simple. If we're keeping the pressure in our lungs the same, right? Because you can only expand so much out. The pressure in the outside atmospheric pressure is lowered, then your difference between the two pressure is going to be lessened. That means less air is even going to come in. Well, if less air is going to come in, doesn't matter, even if you don't change the composition of oxygen. So oxygen is probably no different up there than down here. It's probably still around 20% of the atmospheric pressure. The atmospheric partial. The partial pressure of oxygen is the same as what I wanted to say, around 20%. Then if you're breathing less overall air, so less delta P mean less total air, then you're gonna less oxygen being taken in. Okay, so that's just less oxygen being taken in overall. That has nothing to do with the equilibrium itself, though. Okay, so that's the biological perspective. But I think what they wanted to talk about is the result. As a result of this lowered oxygen, what are some biological effects on the organism? So those are the symptoms I was talking about, right? So you can kind of look up at the symptoms of a high altitude sickness. So let's see what that even is. High altitude sickness. Probably fatigue is definitely one of them, easily fatigued, because we see that less oxygen means less final electron acceptor in that Krebs cycle and the whole cellular respiratory equation, which means you have less energy made, less ATP made. Less ATP made means less energy for the cells to do its proper function, leading to fatigue. So I see. So right here are the common symptoms. We have headache, nausea, vomiting, dizziness, lightheadedness, weakness, fatigue, difficult sleep, loss of appetite. And then some of the worst ones, you can start hearing stuff. Coughing, fever. Yeah, and I guess you can somehow link that to lower blood oxygen level. Yeah, because that have a wide range of symptoms when you're lacking oxygen. Say that one more time. Yeah. Yeah. Right. Yeah, and you can review your lecture note. Let's see if they have more things to talk about, and maybe go into your textbook as well. Because when they talk about, just go to any section with Lachette's principle, when they list out all the different external impacts. Because remember, Lachette's principle is trying to counteract the disturbances, right? They give you different types of disturbances. I think the first one was concentration. I'm just going to scroll up right now to see, because we definitely wrote that somewhere. Decide with more gases when you lower pressure or increase volume. When you increase pressure and lower volume, it has the opposite effect. Then you want to shift to the side with less gas. The way I reason in my head is always with volume, right? If you have more space, you want more people in it to fill it. And when I say people, which states of material is able to spread itself the furthest away from each other? That would be the gases, right? So I'm talking about, I want the side with the most moles of gases, because sometimes you're gonna have gases on both sides. Okay, I realize we covered quite a bit. I don't know where we wrote this. Maybe we didn't write it down? I thought we did. I thought we went over the, yeah, but you definitely have some kind of sheet that summarizes the different effects, right? Like the different yeah, actually no, we wrote it right here. So the factors would be concentration, right? So concentration, we wrote that if you increase the concentration of the reactant, it's going to shift towards the product. If you increase the concentration of the product, it's going to shift towards the reactant. And for temperature, you're basically going to write heat into the equation. And when you increase the temperature, you're trying to counteract it by moving to the side with no heat. And then if you're lowering temperature, you want to go to the side with the heat. And then the last thing we said was the volume and pressure thing. So we always try to, so for example, here I wrote 2 moles of A gas turns into 3 moles of B gas. If I increase the volume from 5 liters to 10 liters, now you have a bigger space. I want to move to the side with more gases to fill it. Therefore, I'm going to shift towards the product here with the 3 moles of gases as opposed to 2 moles. Okay. I'm not sure. Let me see. Did we? Okay. Let me just get back to where we were. We did acid and base, so I told you about the first and second definition. So the Arrhenius equation, well, I call it the Arrhenius equation, versus the Bronsted-Lowry, right? So let's revisit that real quick. Whenever I have strong acid or strong base, and by now you should be able to tell me what are the strong acids. What are the 6 or 7 strong acids again? Yeah, you should have that. Yeah, okay, I'll list them so we can have them. Yeah, okay, so give me something. Yeah, sulfuric acid is good. So for example, H2SO4, that's a good one. Oh, my thing is lagging quite a bit. Yep, so we have H2SO4. What else do we have? That's all you remember? Actually, 3 that are easy to remember are the halogens, except fluorine. Yeah, so HCl, HBr, and HI. So you can remember those 3 right off the bat. Those are easy to remember. You have sulfuric acid, you have nitric acid, HNO3. And then the last 2 are very related. It's chloric acid and perchloric acid. So ClO3 and ClO4. And then that's it. Those are your 4. So when you see strong acids, and bases are easy to remember, anything with OH usually are strong bases. There's going to be an exception depending if your teacher is going to let you know that one or not. But if we have strong acid and base, you can really pick and choose first or second definition. So I'm just going to write it as a first definition. So what that means is if you have HCl, You can choose to just write that as a H plus and Cl. Just break them apart. Because what we're saying with strong acid and bases is that this dissociation is near 100%. 1 mole of this will give you 1 mole of each of the products. So stoichiometry is okay there. No ice table needed. But if we have a weak acid or a weak base, what we want to actually do is write down the second definition. And second definition is proton donor and acceptor, and they always work in pairs. And on the reactant side, if you're just dissociating, it's reacting with water. And water is one of those things that can be an acid or a base. So if I write this in terms of the second definition, I can write HCl again in terms of second definition. The way that would be is you reacting with H2O, having an equilibrium, although I'm going to write this equilibrium as a false equilibrium. It's more towards the right because I know this is 100%. I'm going to get, okay, so this is when you have to figure out. You're saying this is the acid, right? Because water can go both ways. Water can be a base or an acid. In this definition, acid is a proton donor or is it an acceptor? Oh, yeah, it's a donor, proton donor. So if he donates an H, what is he going to have left? And it's not just an H, it's an H plus. We're going to have Cl minus left. And then for the H2O, he received the H plus. Now what is he going to become? He's going to become a hydronium H3O plus. Okay, and it's always a good exercise to identify who is conjugate acid or base. Well, right? So this lost a proton, so he must be the conjugate base. The way you can remember it's the conjugate pairing. It's always acid and base, first of all. You can't have an acid pairing with a conjugate acid. Doesn't work like that. Acid pairs of conjugate base, base pairs of conjugate acid. Second thing is the pairing always differs by 1 proton. Okay, so HCl, if you want to say that's pairing with H3O, that's wrong because they're different by more than 1 proton, right? There's 2 protons plus the oxygen and chlorine is different, right? So H2O and H3O, that is off by H plus, so we can definitely call that a conjugate acid right there. Because if you think about it, Cl would be a conjugate base because bases are something that can accept protons, right? So Cl minus is able to accept H plus, but we know it in this case it doesn't because it comes from a conjugate strong acid, which means you'll never see an equilibrium going back to the left side, which means Cl minus is never going to change your pH. Whereas the H3O, that is the definition of acid almost, right? For us, H3O plus has an extra proton to donate. And our first definition was something that increases your H plus concentration. So that fits with Arrhenius theory, definitely. And then for calculation-wise, we don't have to worry about Lewis definition, but we should know the definition of the Lewis definition. We just don't have to calculate anything with it. Right? So if we're talking about a Lewis acid and base, Lewis acid, so did we ever make some kind of table summarizing those 3 definitions? So Arrhenius is the first guy, right? Arrhenius says that acid was something that increases H plus concentration, right? A base was something that increases OH definition. So that was pretty old. You can see by the name. Anything with something us, that was way back in the Greek era. So you're talking about like mid 1500s or something like that. And then more recently, I don't know exact date, but Bronsted-Lowry, and these two are different guys, Bronsted and Lowry. I don't know if they worked together or they independently came. I think they worked independently. I don't think they even worked together. But I think, okay, my thing is lagging so much, so it's not really coming up properly. Bronsted-Lowry. So according to Bronsted-Lowry, acid is something that is a proton donor, so it donates proton donor, and base is something that accepts proton, so proton acceptor. And that's just to cover the bases of something like NH3, right? NH3 is actually a base, ammonia is a base, but by the first definition, it doesn't work, right? If we throw that in there, wait, there's no OH to give off. There's no OH attached to this. So that can only explain all the OH bases. But Bronsted-Lowry definition, well, we can actually accept the H+. So for example, if we react that with water, it's actually going to take one of the H pluses from water to form ammonium, and then we're going to have OH minus. Oh, there's my OH minus. So that's why weak acid and base, I'm going to write the second definition most of the time. Okay, I'm going to erase that. And then the last definition is why I built this chart in the first place was Lewis. So Lewis says that, wait, no. Protons are not the things that's being donated or accepted. It's actually the electrons. So in this definition, well, if you're giving off H+, if you're giving away H+, that's almost the same thing as gaining a negative, right? Because if you lose a positive, it's like you're becoming more negative. So electron acceptor, electron acceptor, and then base would be the electron donor. Okay, but we're not really going to make any calculation with that third definition. So when you hear me say first definition now, I'm talking about the straight dissociation, single arrow. If I'm talking about second definition, I'm talking about the Bronsted-Lowry definition. I'm talking about a double arrow. So maybe I should actually write a weak acid. So some weak acid like acetic acid, right? The component of vinegar, for example. HC2H3O2. Sometimes you might see it in a different form, right? The CH3COOH version. But okay, let me have you do this one. So if I write that as an equilibrium reacting between an acetic acid, which is the acid, with the water, which I'll give you the hint, but later on you got to start knowing that you're reacting with water. It's the base here. What do I have as the product this time? C2H3O2. Any charges on that? Yeah, we have a minus charge because it's the proton. It's not just the H that's being transferred here, right? It's the H+. So therefore, you went from neutral to now being a negative charge here. And then what happens to my second one? What else do I have as a product? H3O+, exactly. H3O+. Okay, so actually let's continue this, and actually let me give you a problem that's based off of this. So a problem that can be based off of this would be something like this. If I have a certain concentration, so this problem, let me just move that actually down here, but you're gonna excuse my pen. It's lagging quite a bit today. Okay, so let's say we have this reaction here, right? We have this reaction. So this reaction is really just throwing in the acetic acid into base. And this is very common with vinegar preparation. When you buy vinegar at the store, it's 5% acid, which means the other 95% is water. So what's going on here is the acid is donating an H+ to the base. And I'm going to ask you this as a question now. Oh, before I even get to that, what's the conjugate acid and which one's the conjugate base? H3O is actually not the conjugate base because, okay, let's draw the pairing. So H2O pairs of H3O plus, right? Yeah, if one of them is the base, the other one has to be a conjugate acid. It's not even right calling an H3O plus a base, right? Because H3O plus, how can that gain another proton? If you gain another proton from H3O plus, you get H4O plus. That's not something that we study in high school or even early university, okay? So that's off by one H, so we know that's a pairing, and conjugate of a base is going to be a conjugate acid, which means that these two will be a pairing as well. They're off by one hydrogen, so this one will be a conjugate, a base, right here. Okay, so now I'm going to give you the actual problem now. So this question says, what's the pH? And this is the bread and butter problem, right? If they give you a certain concentration of, you know what? I might even get you to calculate that. So I would have pH of 2 liters, if that shows up. 2 liters of sorry, my pen is not working. I'm just gonna give you a concentration. So I was gonna give you actually moles and volume, but you know how to calculate concentration from moles and volume. You just divide them, right? Yeah, that part you remember. Yeah, so I'm just gonna give you the concentration of, how about 0.5 molar, so that's moles per liter, of HC2H3O2. Okay, so how do we begin this problem? We say that we have a weak acid here. So weak acid, I better draw my, I better write out a second definition, right? If it's a first definition, sorry, if it's a strong acid or base, then we can actually use the first definition. But this is weak acid, so let me just copy that equation down, and you can write the equation once because you're gonna have to build this ice table with me one time. Okay, so I'm just gonna copy that exact same equation down here again. But as I said, this time we actually need an ice table, right? We need an ice table. So ice table tells me what's the initial concentration the moment I combine these two together before anything has even reacted or dissolved away. So if I just pour these things into it, water by definition, liquid, does not have a concentration, so we can just get rid of that for now. We have 0.5 molar of the acetic acid. Well, when I just pour that in, do I have any acetate? Do I have any hydronium? I have nothing, right? So those concentration was initially 0 because I have just poured the acid into my container. All right, you got that part. And then what are my changes then? That one's is according to mole ratio, right? So this is the same thing as equilibrium, last chapter stuff. So it's according to the mole ratio. So then the acetic acid is going to subtract by X. And that's because the balance equation is 1, 1, 1, 1. They're all ones. If you see a 2 in front of it, that would be minus 2x, right? Because they're saying for every X amount that's taken from the acid, you're going to gain an X amount for the acetate, and an X amount for the water. So we have minus X, we have plus X, we have plus X. So what does that give me at the end? At the end, I have 0.5 minus X. I have X here, and I have X here. And of course, I forgot to give you the Ka because we do need to find the Ka. Actually, you can find that. Do you have a table somewhere? Okay, so maybe open up your textbook or, Google in Ka table. So you should find that fairly easily. And I'll go find a value as well on Google. So, and Ka would be called the acid dissociation constant. And you remember, equilibrium is K, and then whatever letter at the bottom right, we're just trying to make it as a special relevant to my actual equation. So KSP was the dissociation of a salt. So Ka is the dissociation of an acid. All right, did you find that table yet? Still there, Yuki? Yuki still there? Oh, okay, yeah. I think we lagged out for a second there. Yeah, did you find a Ka table that has acetic acid? Yeah, so what is the value? Yeah. Okay, and that is actually going to be a value you're going to see again and again and again because the number one most popular molecule in the acid and base chapter is acetic acid and ammonia. So those are like famous examples of weak acid and weak base. I don't know why they always, I guess that's the most common. Okay, you know what to do from here. What do I do from here? How do I find X? Because if I can find the final concentration of the H3O plus, then I can just use the pH equation to find that. So how do I build an equation to solve for X? Well, let's write a Ka equation, right? Ka is just going to be all the product raised to their coefficients, and in this case they're all just ones, divided by all the reactants raised to their coefficients as well. So these all coefficients are all to the power of 1, since the balanced chemical equation all has 1 in it, right? And then we can just fill in their final concentration. So we have X here, we have X here, so X times X all over 0.5 minus X. And luckily, we don't have to do a quadratic equation if what? How can we avoid this quadratic equation here? I'm looking for a special rule here. How about the 500 rule? I forgot if you do the 100 rule, 500 rule, 1000 rule. Do you remember that? They say if the concentration, if your initial concentration of the acid or base, the thing that's being dissociated, in this case 0.5, if that's greater than your Ka by more than what was yours, 100, 500, or 1000? Let's make sure we remember that, because different teachers do it differently. I've seen all three of them. I go by 1000. Are you looking for it? Okay. It should be in the last chapter, but it doesn't matter. Let's just go with 500. We'll go for the middle. So I'll just say 500 for now, but you know how this rule works, right? Remember we said if 0.5 is greater than whatever threshold that they give us, if this is greater than 500, and it is, because 0.5 is 10 to the negative 1, you know, if I just look at the magnitude wise, 10 to the negative 1 minus 10 to the negative 5, we're at the order of 10 to the 4. So no matter what, it's going to be bigger than 1000. If that's the case, so I can write that, since that, therefore, the thing applies, the rule says that 0.5 minus X, then I can pretty much approximate that to be 0.5. And that's going to make my math a lot easier, because that eliminates the C term. Okay, so as I said, let's say that one more time. If your initial concentration of the acid or base that you're dissociating is greater than the dissociation constant by more than 500 or 1000 or 100, whatever that number is for your teacher, then we can say that the X is pretty much so small that 0.5 minus X is pretty much 0.5. Because imagine if X is like 0.00000 something, right? 0.5 minus that is going to be 0.499999 something. And along with the significant digits, that's not even going to touch the number at all, right? It's going to be the same number. So we're basically simplifying this to be 1.8 times 10 to the negative 5 x squared over 0.5. I mean, quadratic is not that hard either. I mean, you could definitely ignore this rule and just solve it using quadratic if your calculator has a quadratic solving function, right? Probably takes like 1 or 2 more steps of expanding out. Okay, so here if you solve this, then it's simply 1.8 to the power of negative 5 multiplied by 0.5 and then square rooting that. Okay, and that's the thing I said last time. Don't just go and reject the negative number right away simply because it's negative, because X can be negative, because X is just talking about a change, right? What can't be negative? Okay, so let me just write out the x1, x2, because when you square root, you technically have the positive and negative version. So what I'm saying here is the change can be negative, because right now we're saying the changes are negative X for the reactant and plus X. If the X turns out to be negative and it works, and it's not something reject, it just means we predicted it wrong. It means that reactant was supposed to be the one that increases because negative negative is going to make a positive. And then the product is the one that's actually going to be consumed because positive negative is going to make negative. What can't be negative is the final amount there. So the column with the E. So because in this case it's X for the acetate and X for the H3O plus, that's why we reject the negative. Because if we sub those in as the end, we can't have negative concentrations. So again, the change can't be negative, but the ending concentration cannot be negative. And that is the reason why we reject it. Not because X is negative. So don't go and reject it right away. Sub it back into the end and see if that will give you a negative. And again, I just want to give you a scenario when that would be possible. That is possible if you started off with some acetate ion already. So that's in the last section with the buffer solution. Because buffer solution, you're going to start with some acetate and some of the acetic acid. Because by definition, buffer contains both the acid and its conjugate base, or a base with conjugate acid. Don't worry if you didn't get any of that in your head. We'll cover that stuff in the last section. But right now, let's continue this problem. So if we're saying X is equals to that, we're also saying that H3O has that concentration, right? H3O plus. And I think you can take over from here pretty much. Because if we have the H3O plus, how do we get the pH? You can tell me the steps to get it, so I'll leave you alone to do it. Yeah, so I just wanted to hear pH would just be the negative log of whatever that H3O plus is. Because the equation is pH, P of something, power of something, it's just negative log of, that number. So negative log of that, negative log of the answer, that's going to be, yeah. So, wait, say that again. Oh, wait, yeah, so what is the pH then? You got. Yep, what'd you get? Oh, for your X, why? So you did 1.8 times 10 to the negative 5. You multiply that by 0.5. I think that's the same thing as the problem as last time. What did you get in this number? I think this is the step that your calculator messes up. And you have to remember that. What do I have here? What did you get when you do 1.8 times 10 to the negative 5 times 0.5? You probably got a crazy number, and I'll tell you why. Okay. Wait, I think, wait, let's talk about that though. I think what happened was your calculator thought it was 1.8 times 10 to the power of negative 5 times 0.5 up here, right? Do you think that's what they did? Okay, well, if it's down, then it should be okay, because if it's down, if you made it down, then it really doesn't matter if you multiplied the 10 to the negative 5 by the 0.5 first, or if you multiply it by 1.8 first. But either way, just be careful, right? When you actually do the problem, just make sure you keep clicking enter before you get to the next step. Anyway, so using these ones, can you see if you get the same pH as me? Okay, yeah, so 2.52 is going to be the pH, which is low, but not that low, right? Because we can make the comparison. Let's say we had, here, you make the calculation this time. Let's say if I have pH, I'm asking for pH of 0.5 molar, so same concentration, this time HCl. Okay, how would you do this problem? What is the equation? What is the chemical equation I should even write out first? Yeah, for HCl. No, this is just me trying to remind you, when you have a strong acid or strong base, don't even write the second definition out. It'll be a waste of time. Just write the first definition out, which is HCl just breaking apart into H plus and Cl minus. Because what I'm saying here is I can use stoichiometry here, because I don't have no change, or I don't need to know. I know what the change is. It's going to use all of that up. So here's a fake ice table. Here, I'll build you the fake ice table to see. You've been using ice table all along. It's just you didn't write out the ICE. Let's just wait 1 second. Yeah, so in this case, this is a stoichiometry ice table because I know exactly what change that is. It's minus 0.5 molar, right? And then I know this is 0. I know this is going to plus 0.5 molar, plus 0.5 molar. So I know I have 0.5 molar, 0.5 molar, and 0. You did this in grade 11. You just didn't put an ice on that, right? We only put ice for the equilibrium stuff, right? So this is almost like a stoichiometry. So in this strong acid, then we can just, see the calculation a lot simpler. We can just go right to the pH. It's going to be equals to negative log of 0.5 molar. And you can compare that to the last answer. So same concentration. One is a strong acid, one's a weak acid. In this case, we have negative log 0.5. See, that's a much lower pH. And if you say the numbers, well, the numbers are kind of similar. Just remember pH scale is off by 10, right? Every number is off by 10 times as more acidic. So this is 0.301 as the pH. So that's a much more acidic solution than something that's 2.52. All right, do you want to do a weak base problem? Okay, so I'm going to ask you still the same thing. Bread and butter problem. What is the pH of something? What is pH of, let's do 0.5 molar again, but this time NH3. Okay, be very careful when you go consult the table this time. What you need is a Kb value, and sometimes the equation don't actually give you a Kb value. You have to use this equation here. Ka times Kb equals to a constant, which is Kw. Okay, and I'll go into a little more detail of this. This is called autoionization of water. But right now, just know this. If you have Ka, you can find Kb because they relate to the fact that they multiply to be 10 to the negative 14. So what that means is to find Kb, you just need to take 10 to the negative 14 divided by whatever they tell you its conjugate acid is. Okay. But that also requires you to kind of know what the conjugate acid of the base is. Sorry? Yeah, it's almost the same thing, but you need to find the Kb instead. And once you calculate at the end, there's another trick to it. So I'll wait for that surprise. See if you can figure it. What does the chart give you? No, I mean like when you find the pH at the end, there's an extra step here. Oh, they actually gave you the Kb in the table? It says Kb? Okay, then you can use that. But it's not going to be the same pH though, right? I hope you recognize that. Because let's write out the equation this time, right? So NH3, what's the equation? I'm reacting with what? Water. What do I make that equilibrium with? Yeah, just think about what is my base? Like, is NH3 a base or an acid? Because if that's a base, your water's got to be an acid. If that's an acid, then your water's got to be a base. So if it helps, we should label that. So you should know that this is a base. So that would make the water the acid. So that if you label that, that might help you figure out what the products are. Yep, so what do we got here? So if NH3 is the base, is it going to donate a proton or is it going to accept a proton? I think you are cutting out again. Oh, you have lagged out. Alright, let's just wait for her to be reconnected. Okay, if it disconnects one more time, I guess we can try Skype instead or something. Okay, yeah. So have you figured out what are the two products for me? No, I didn't hear. You got cut out already. Yeah, NH4 plus, NM plus, OH minus. So always give me the charges. All right. So if we build this ice table, so this is what I mean. When you find the ending for this one, it's not the OH plus concentration that we found, right? It's not the H3O plus anymore. This time it's the OH. So when you take negative log of that, you are actually looking for POH first, which means you have to, and you know how pH and POH relate. So from POH, you can calculate back to a pH. So see if you can do that for me. And tell me what that value is going to be. Yeah, POH is also negative log. Yeah, do you know how to convert that? Do you know the relationship between pH and POH? Say that one more time. What? They add up to be 14. So pH is going to be 14 minus POH, which means in this case we have 14 minus 2.52, 11.48. So let me know when you have that one down. Okay, so one last thing I want to talk about before we work on maybe some of your material is the autoionization of water. Autoionization of water. And while we're on the topic of water, I want to give you this definition of this word here called amphiprotic. amphiprotic. So when I say amphiprotic, I'm talking about something that can act as a base and an acid. Oh gosh. What just happened there? Okay. That is not what I wrote. Amphiprotic. So something that can act as acid and base. In other words, it can accept or donate a proton. So that's water. So that's something like water. So for example, that's something like water, because water can gain a proton to get H3O plus, or lose a proton to give you OH minus, or another example would be HSO4 minus. So imagine this is basically the conjugate base of the sulfuric acid. So if you start off from sulfuric acid, you lost one proton, but guess what? This guy can now gain the proton back. Well, technically not really, because that equilibrium doesn't lie that way. But theoretically it can. It can gain the H to get back to sulfuric acid, or it can lose one more proton to get to SO4 2 minus. So those are amphiprotic. So something that can act as both acid and base. Autoionization of water says this: if you have H2O, if you just have a glass of pure water lying somewhere, glass of pure water, some of that water actually autoionize itself in such a way that you have H2O plus H2O. One of them is going to act as an acid, which means the other one's going to act as base. Very minimally though, very little bit of it's going to act like this. So if H2O gains a proton, then it's going to become H3O plus, and then one of them is going to lose a proton, you get HOH minus. So here, if I were to call this equation a KW, it is experimentally found that it's equals to 1 times 10 to the negative 14. And if I actually write out that equilibrium equation, it will be the product raised to the power of 1, OH minus raised to the power of 1. And guess what? There's no reactant because they're both liquids. So you don't put them in the actual equation. So this is where I derived that equation earlier. The concentration of H3O plus and the concentration of OH minus is going to give you 10 to the negative 14, which means yeah, so we can also say that Ka times Kb is going to be equals to negative 14. Okay, so why don't you gather the questions that you might have? We're going to take a 10-minute break, and then we're going to come right back for more chemistry. Okay, all right, see you in 10 minutes. Okay, I'm going to go wash them. Alright, and we are back. Alright, did you find some questions for me? Okay. Want to share screen? Oh, have you been sharing screen this whole time? No, you have not been sharing screen. Yeah, let's share screen and then I can see what you're seeing. Yep, I see it now. Equilibrium of weak acid and base. Yep, so there is... Yep, so there's that water ionization thing I was talking about. So that's the H2O plus H2O giving you H3O plus and OH minus. So that's the autoionization, so just water reacting with itself and a pure water solution. Yep, so if you go down, it says because water dissociate, it has an ion product Bronsted. So we call that self-dissociation. We call that specific equation Kw. So Kw is only when water is reacting with water. Okay, and it has a constant value of 1 times 10 to the negative 14, and that's specific to STP. So at different temperature, as you said, you know that from last chapter, temperature affects the direction of the equilibrium. Okay, so that's all that. So that's 10 to the negative 14. So what's useful about that is that basically derives the relationship between Ka and Kb, and the relationship between H3O plus and OH minus. Because imagine, from this equation, this actually gives us the fact that, so look, using this equation, we can actually derive that if I negative log both sides, right? If I negative log both sides, okay, so negative log both sides. On the left side here, negative log of 1 times 10 to the negative 14, which is just negative log of 10 to the negative 14. Well, you know the log and the 10 to the power of will cancel. You know this from math. This will just be 14 because the negative also cancel out with the negative. So we have positive 14, sorry, equals 2. On the right side, we can split that into, remember, this is just negative log of H3O plus negative log of OH minus. And that's because of another property of log, where if you do a log, you get log, so I should actually put a bracket around that, log plus that. So the way that works is log of AB is really just log of A plus log of B. You know that from advanced functions. So 14 therefore equals to negative log of H3O plus, that's just pH. And then negative log of OH, that's just POH. So from that, that's also where you got the 14 equals to pH plus POH from. So it says, so at pH, H3O is going to be OH minus. It's going to be right in the middle. See, that's why at pH 7, it's, they're both concentration is going to be 1 times 10 to the negative 7. Alright, so that basically gives you the shortcut between the two. So it says you have 2.5 moles per liter HNO3. So this problem shows you that this is a strong acid, because you should have your strong acid memorized. That's why I said that's the first thing you should be able to do. So if you did that, you would have recognized that nitric acid is indeed a strong acid. And if it's a strong acid, don't bother writing the second definition. You just have a nitric acid dissociating into a H plus and NO3 minus. Okay, so if you have, so I can just skip to that. If you have 2.5 moles per liter of this, that means you have 2.5 moles per liter of this, because this is a 100% dissociation. So from this, you can basically do a negative log of that. And then if they want POH, then you can do 14 minus that. I think they want you to find the OH concentration and the H3O plus concentration. So H3O plus concentration, we got that already, is 2.5 moles per liter. Alright, so if that's 2.5 moles per liter, so we can use that equation we just derived earlier. Kw is going to be the concentration of the H plus times concentration of the OH minus. Okay, if my pen's going to work. Yeah, so we have 10 to the negative 14, which is Kw. So that's Kw equals to OH minus times H3O plus. So therefore I have OH minus is the one I want. I can sub in 2.5 molar. So therefore it's just going to be simply 10 to the power of negative 14 divided by 2.5. And the OH concentration is going to be 4 times negative 15. I wouldn't go through this if they ask you for pOH though, right? Because pOH, you should actually just find a pH and 14 minus that. I mean, this works too. Just saves you one step. Okay, so you should know those equations. So if you want to find all those equations in one place, all those things that derive from Kw, here it is. So all the things that come out of the autoionization equation, H plus and OH minus concentration, they add up, so they multiply up to be negative 14. Then the thing that comes out of that is that pH plus pOH gotta be equals to 14. And also, in relations to Ka and Kb, Ka times Kb also equals to 10 to the negative 14. And then finally, pKa plus pKb, which we'll talk about in a second, so you don't really know what pKa and pKb is right now. That's more relevant in chemistry as well. It's just negative log of Ka, because you know P something is always negative log of something. So pKa would be negative log of whatever Ka is. But I'll go through what that means when we get there. So those are the 4 equations that kind of comes out of the autoionization of water. And you can kind of use them. Yep, so what is Kw? Yep, so that's the 10 to the negative 14 part. The acid product constant, okay, so they're calling it an acid product constant, so is a measure of how much an acid dissociates in water. The acid dissociation constant, oh, what, are they different? Okay, I don't know what the acid product constant is. I'm assuming it's pretty much the same thing, because that is measuring how much the acid dissociates in water. I think they just meant acid dissociation constant. So you have H3O plus times A minus over HA, and again, raised to whatever coefficient they have. And H2O is not included in there because H2O is a liquid. As Ka... No. I think they meant it's the same thing. I've never really heard of acid product constant. I can look that up real quick. Acid product constant. Oh, bless you. Yeah, I think that's just the acid dissociation constant. Yep, so as Ka increases, the acid dissociates more and more, right? That's why strong acid, by definition, there's not really even a K value. K is just really large or infinite. Because if you have 100% going to product, then when you write that equilibrium, you're going to have no reactant. Reactant is 0, divided by 0 is undefined. That's why there's not really a K value. And if you check the Ka table, the strong acids will either show up as really high values or just none at all, or just be a dashed line. Alright, so let's do this problem. Propanoic acid is a weak monoprotic acid. Monoprotic is just a fancy way of saying mono means one, protic means the proton that it can dissociate. So monoprotic just means there's only one proton that can be detached. So that's different from something that's polyprotic, maybe something like H2SO4. You see there's two protons that can be dissociated there, so those are called polyprotic. Or in this case, it'll be a diprotic because it's two specifically. And maybe something like a H3PO4 would be a triprotic because you see there's three protons that can theoretically be taken up or donated. Alright, so this problem says 0.1 moles per liter solution has pH of 2.96. Find the Ka and the percent dissociation. Let's not worry about the percent dissociation first. Let's find the Ka. Alright. So we should probably begin by writing a second definition equation for this because this is a weak acid. So we're going to write this reacting with what? Who is it going to react with? Water, exactly. And then what are my two products going to be? Yep, and start saying the minuses now. So that's a minus and then plus. H3O plus, perfect. So what we're going to do is build an ice table. And probably we're supposed to have all the values for the end there, right? Because how else are we going to find Ka if we don't have all of those values? So let's go back. We have 0.1. So we know this is 0.1. Okay, just gonna have to bear with me for a second here. My pen is lagging. Okay, we're good. So we're gonna have 0.1 molar here, and as we don't have anything to start because we're just pouring that in, so minus x plus x plus x. So we're probably gonna be able to find out what x is. So for now, I'm just gonna write 0.1 minus. I'm not even gonna write x because I know I'm just gonna erase it and fill it in later. Well, how can I find x? Well, they gave me pH. They told me that pH is equals to 2.96. From pH, we can probably get a concentration of the acid, and that will basically be my concentration. So you're going to turn that into a H plus, and that H plus is basically my final concentration. Because remember, the last problems we did, we basically found out what this X is, and then we plugged it into the negative log times, negative log of H plus. So this time working in reverse. So working in reverse, pH is going to be 10 to the power of negative. Sorry, I wrote that wrong. I meant to say H plus concentration. H plus concentration is equals to 10 to the power of negative pH. And what did you find for that? Okay, perfect. So 1. Yep, that's correct. So 109. 1096, and that's a molar. Okay, so now what can I do? So if I know that this is x and that is equals to 0.00196, that means this is also 0.00196, and it also, so I said it again. 1096, yeah, 1096. So 1096. Okay, so what would be the ending concentration? It would be 0.1 minus 0.001096. Probably not big of a change, but you know, we'll consider that anyways. So we're gonna write that as 0.0989. Okay, so now what can we do with these values to find Ka? Yeah. Yeah, so you can Ka is equals to your concentration. I'm just gonna write A minus right now to represent acid. So if you ever get lazy, you can write A minus as the conjugate base, and then HA as the acid. So HA, if this is the acid, A minus must be the conjugate base, and then multiply that with the H3O plus. Alright, let me see what I get. So 0.001096, we're going to square that because we basically have two of those, and then divide by 0.0989. What did you say your number was? Yep. Yep, that's what I got. Okay, so now let's move on to that. So everything good so far for this? Okay, so that's a 1.21 times 10 to the negative 5. Okay, next problem says, well, next part of the same problem says what is the percent dissociation. So now it's the percent dissociation. Okay, so think back to my strong acid equation. So if I have a strong acid, HA of a strong acid, I'm going to dissociate that to H plus A. Think about it like this. 0.5 in this strong acid is going to give me how much H plus? This is a strong acid, so I'm just writing you a strong acid. So I have some kind of strong acid, and a strong acid such as maybe HCl or something. How much H pluses is that going to make me? So let's say right here, 0.5 mol, 0.5 exactly. And that's because this is 100% dissociation. Okay, so I'm just hinting at you. How can I represent this as 100? What should I do to it? I should just consider the acid, because in order for me to get 100, it's probably 0.5 divided by 0.5 times 100. And that will give you 100% dissociation. So all I'm trying to say is percent dissociation is really going to be your H plus final. So H plus from your, ending from the ice table chart divided by your original amount of H acid or HB or whatever, and that's from the I. Okay, so in this case, which means I'm going to divide 0.001096 by 0.0989, and of course that's going to give you a decimal, so we should multiply that by 100 to get in the percentages. So I'm going to write that in as well. So think about this as, so think from the strong acid perspective, right? 0.5 molar generated 0.5 molar. That's 100%. Here I'm saying 0.1 molar generated how much of the acid? How much H plus was generated from that? Well, 0.001096. If 0.1 made 0.1, that would be 100%. So who do you think should divide by who? Well, we're going to divide the smaller number by the bigger number, or the amount of acid that was dissociated from the original acid. So we're going to go 0.00. So it's going to be 0.001096 divided by 0.1. And of course, we're going to multiply that by 100. And that is going to give me 1.096%. So look, the Ka of, what was the Ka for this question? Ka of 10 to the negative 2. So that's not even that, wait, no, that's not the Ka. Ka is 10 to the negative 5. So 1.21. And that's pretty close to acetic acid, right? Remember, acetic acid last time was 1.8 times 10 to the negative 5. That's only a 1% dissociation. You put 1 mole of that, only 0.01 mole is going to be of acid is going to be broken apart. So only 1.096 of that molecule are actually broken apart into the H plus and its conjugate base. Does that make sense? Okay. All right, you got that? All right. And you understand when I said H plus and H3O is interchangeable in this chapter, right? H plus and H3O plus. They're both talking about proton, yeah. So that's why sometimes I'm writing, I know I've wrote H plus here. H3O is probably a little more appropriate, but I'm kind of interchanging between the two. Okay? All right, what we got next? Let me see. So we got find the concentration of H2PO4 minus. Is that a strong acid or no? Yeah, H2PO4 minus is not a strong acid, but actually, yeah, they're none of them are strong acids because strong acids don't even have a phosphorus in it, right? It was the halogens, nitric acid, sulfuric acid, and then chloric acid and perchloric acid. Okay, so it says find a concentration. Here, let me just copy paste the problem onto here. Okay, so here's the example problem. We have here, it says find the concentration H2PO4 and the pH of a 0.35 molar solution of H3PO4 at equilibrium given that it is polyprotic. And polyprotic, I mentioned earlier, it's the counterpart is the monoprotic. Monoprotic means one proton gets to dissociate. Polyprotic means multiple proton gets to dissociate. So this is what they're saying. Why did they give you two different Ka value? So let's begin with the beginning. Let's start off with the beginning. We begin with a phosphoric acid, so H3PO4. Okay, let's write out the first dissociation. So what am I reacting with again? Okay, plus H2O. And then we're gonna get an equilibrium with who? Yeah, H3. Yeah. Well, what concentration did they give you? It's the H3PO4, right? They say find the concentration of H2PO4. So you start with H3PO4. Yeah, H2PO4 minus plus H3O. Now, so that Ka, that equation, they're telling you the dissociation constant is 7 times 10 to the negative 3. Which is not too bad, right? 10 to the negative 3. So you should start getting familiar with the value ranges now. Last time we said 1.2 times 10 to the negative 5 is about a 1% dissociation. So this is probably something higher than that. All right, so now, why did they give you 2 Ka value? And that's because if you take the product of this, which is the H2PO4, you can actually dissociate one more time. So you have an H2PO4 minus. We're going to react that with water once again. And this time, what do we get for the products? Okay, we get HPO4. And what's the charge on that? 2 minus, right? Because you lost another H plus. And then plus H3O. Because we're not reacting with H3O plus. We're reacting with water again. Anytime with dissociation, second definition, we're always reacting with water, right? Well, not always reacting with water, but because later we're going to see acid and base that does not necessarily involve water. So Ka of this, they're saying this time it's a bit lower. So this one is going to be dissociating at 6.3 times 10 to the negative 8. All right, so there we have it. So what they're saying is this. If we begin with a certain concentration of that, and actually I might even move this down a bit. I'm gonna move this guy down so we can build an ice table for that first equation. Okay, so but qualitatively, I'm just gonna show you what's going on here. We threw some phosphoric acid into our beaker or bucket or whatever, right? It reacts with water, or you can think about it as, you know, it breaks up apart into H2PO4 and, you know, an H plus. In this case, you know, it's donating a proton to water, so you get the H3O plus and the H2PO4 minus. But it's saying some of those H2PO4 actually breaks up even further into HPO4 2 minus and H plus, or in this way we can think about it as it donated a proton to H2O. But I just want to think about it dissociating. Sometimes it's easier for your mind to understand than donating it to a water, right? And in this case, there's unlimited water, so to speak, compared to acid and base. So therefore, you get this two steps here. So you have this first equation that's creating some of that H2PO4, and in the second equation, you're going to use up that H2PO4. So that balance between those two is how you're going to figure out kind of what your H2PO4 minus concentration is going to be. So let's build an ice table for this first. So for this first step, we have some kind of initial. So what should I write as the initials? What should be the initial H3PO4? Yeah, they gave it to you in the question stem there. Yep, 0.35. So we got 0.35 there. What about water? Trick question. Nothing, because it's liquid, right? Yeah, nothing for the waters. H2PO4 minus. Yep, 0 and 0 for the acid as well. Okay, and then the change should be quick, right? We just minus x plus x plus x, just make sure it's balanced. And most of these cases, these acids, they will be balanced. So we have 0.35 minus x, and then we have x here, and we have x here. Okay, we can go ahead and solve that one time, right? We can go and solve that. Right, we have Ka. Yep, 7 times 10 to the negative 3. So it's going to be x squared. And then you can evaluate whether you can use the 500 rule or the 1000. So make sure you remember to figure that out. So if you take the initial concentration, 0.35, you divide it by the Ka, 7 to the 7 times 10 to the negative 3. We find that it equals to, oh, actually it only equals to 50. So don't use the, it doesn't even pass the 100 rule. So therefore, we cannot do the simplifying. So we actually have to do a quadratic equation here. So we go 7, top negative 3. Okay, don't make the same mistake as last time. I forgot if it was you. I think it was you. Just make sure the A, B, and C corresponds to x squared, x, and C, right? I know I have it written as the reverse order. I have the C plus bx plus ax squared right now. So just make sure when you punch into your calculator for the, if you're using its quadratic functions, you make sure to type in the A, B, and C correctly. Probably did something wrong then. What did you get? What did you get? Fraction plus decimal. What is it? Like, actually, give me a approximate number, like decimals. No. 7. Well, 7's not gonna work because, okay, what you need to. What did I say? The restriction, it does not come from what the actual x is. Is when you plug the x back into the end point, right? With the 7, 0.35 minus 7 is going to give you a negative concentration. That's not a valid solution. Right? It will be valid for the x's, because if you sub in x as it is, 7 is good. Okay, let's see what you did. So what did you write as the K8? Look at my Zeitboard. So I wrote 7 times 10 to the negative 3 is equals to x times x, which is x squared, over 0.35 minus x. Okay, I multiplied the denominator on the right hand side over to the left. So make sure you distribute them, right? You distribute, there's a distributive property in there. So 7 times 10 to the negative 3 times 0.35 give me that 2.45. And then what about the negative 7 times 10? Yeah, you forgot to distribute it. Oh, you did? Then what did you do wrong? Oh, okay, so you put positive 7 times 10 to the negative positive 1. Where's 1? You times times 1, so you just combine those two together. Yeah, that's a separate term. Yeah, that's an x term. Oh, okay. It's a neg. Oh, you just put 1 instead of negative 1. Yeah, so your A should be negative 1. Your B should be negative 7 times 10 to the negative 3, and then your C should be 2.45 times 10 to the negative 3. Yeah. Yeah. So we're not rejecting the negative 0.0531 because it's negative. It's because if we sub it back into the equation, well, the 0.35 minus 0.053 is okay because we're still going to end up with positive. But the x, so the concentration for x30 would be violated, right? Because those can't be negative concentrations. So that is the reason why we reject it. So we can go ahead and reject that. So we can keep this. That means we have 0.046. So does that mean my final answer is that I have 0.046 molar of H2PO4 minus? No. Then that's because we have to go through another protonation. Okay, so if we do another deprotonation, this time how much do we start off with H2PO4 minus? How much of that do we have? Yes, great, because we bring that from the last one. Let's see, did we round off any numbers from that? Or was that the actual number? It's much longer. Maybe we should take one more digit. Yeah, okay, yeah, let's take that. Let's take one more. 0.0461. Okay, again, the water can be gone. We start off with we do start off with some kind of H3O plus this time, right? So we have 0 of the HPO4 2 minus. We haven't made any of that yet. But from the last question, we already made some H3O. So there's some H3O swimming around in there already. And that's going to be 0.046 as well. 61, I believe. Yeah. So remember last equation? Wait, is that a okay or is that a what? Oh, that's okay. Okay, I heard what? Okay, so then we're gonna go minus x. We're gonna go plus x. We're gonna go plus x. Okay, same deal. 0.0461 minus x. This time, this one is x. This is 0.0461 plus x. And then we're almost there because, you know, whatever we get for the final one here, that is going to be my H3O plus concentration and also my HPO4 minus concentration. Okay, so we're going to go with the Ka value again. If my Zeitboard actually is going to respond. Okay, maybe you can go ahead, go forward without me. Yeah, because this is the Ka2. It's the second deprotonation. So sometimes some Ka tables is going to give you those separately on, or maybe onto the same table. So Ka in this case is going to be 0.0461, and I'm pretty sure this time the 100 rule should apply because that is quite a small Ka. So anytime you get a small Ka, most likely you can use your shortcut there. So this time we're basically checking with the 0.0461. And just by the looks of it, right, 0.04 is 10 to the negative 2, 10 to the negative 8, and 10 to the negative 2. That's going to give you 10 to the negative, 10 to the positive 6. So that's probably greater than 1,000. That doesn't confuse you, right? The 100 rule or 500 rule, 1,000 rule. Yeah. So yeah, so you get why we can use the rule here this time and not last time. Yes, we're saying x is so small, 0.0461 minus x is pretty much 0.046. But that's not valid last time, right? Because look, last time was 0.046. If you say that 0.35 minus 0.046 is roughly 0.35, that's a huge stretch. Because if you do subtract it, it's actually going to be closer to 0.3 instead. So that is going to be in an accurate approximation. So after we solve for x here, I'll show you that x is so small that 0.0461 minus that is still going to be about 0.0461. Whoops, I made a mistake here. This should be x. Yeah, so this just simplifies to be 0.0461 minus x. Let's see. I doubt it. Yeah, I doubt it. Yeah, I doubt it. I think it should be quite small, actually. So what did you get for x? .389 times 10 to the negative 5. Okay, so then now you can go and find out the pH and the HPO4 2 minus. Wait, was that what they wanted? No, they wanted the H2PO4, yeah. So you want to go in and plug it back into the ends, and then you can report me back for the final answer there. Yeah, you want H2PO4, yeah. So 0.0461 minus whatever x you just found there. Sorry, wait. What did you get? Give me 1 second. I'm going to... Wait. Where did you get 2 point something from? I got 6.3 times 10 to the negative 8, which is just the Ka value, right? Look, Ka equals to 6.3 times 10 to the negative 8 equals to the 0.0461 plus x times x over 0.0461 minus x. Yeah, so look, I'm saying that I can just ignore the plus x over here. I can ignore the minus x over here, right? Because we're saying this is pretty much equals to 0.04. This is pretty much equals to 0.04. Look, can't these two just cancel then? So if they cancel, then you just have x equals to 6.3 times 10 to the negative 8. Where did you get the 2 point something from? Stay with me, Yuki. Oh, I think you just got cut out for a second. Did you say something? Use what? Oh, what the hell? Wait, did we calculate this wrong from that first step? Because I think we did something wrong. Because I'm just looking at their solution. X should actually be 0.16. Wait, you're not sharing your thing anymore. Can I see your... Can I see your share screen one more time? Yuki? I think you're cutting it. Okay, wait, 0.35 minus x squared. No, not yet. SSU. Yuki Wang has started screen sharing. Okay, I see it now. Yeah, because it says x1 should be 0.16. Unless they are wrong. But I don't see how we could have made a mistake there. There's not much room for mistake there. Maybe I'll punch into calculator one more time. Minus 1 minus 7 e negative 3 2.45 e negative 3. Yeah, it should be 0.046. So why are they telling me 0.16? Well, it doesn't matter because our x2 is right. So let's just move forward for now. Let's see if we get the same, because if we get the pH is 0.8 and H2PO4 as 0.16, then we're good, right? So, wait, are you still with me? Because you keep signing out of the sideboard and Zoom. Okay, I'm just gonna wait till you come back first. Oh wait, I just heard you a bit. Should I just call you on FaceTime? I'm just gonna call you FaceTime to finish up this lesson, because this is not 2. Okay, okay. All right, let's just wrap this up. So are you still on the Ziteboard? Because I saw you you kind of lagged out of that as well.
Why is your sound so staticky?
Staticky. What about now?
Yeah, you're good.
Okay.
Are you on a fan?
No, I put it on the MacBook. Probably interference with the MacBook or the fan that's on that. Okay, where were we? Yes, let's just wrap this up. So, wait, can you see the Ziteboard or no?
Yeah.
Oh, you can? Because I don't see you on here, but as long as you can see it. So the last thing we need to find is this, right? Because they want to find the H2PO4 minus concentration. So that will simply just be 0.0461 minus whatever X we just found.
Are you lagging or is it just not showing up for me?
Probably just not showing up for you. So you know what? I'm just going to share my screen instead. So I'm going to share. So I am going to share desktop 2. Okay. So this should be faster this time. Apologize for the internet connection today. Is that better? Can you see all those words showing up? So
the last thing I see is the ice table.
Even on the share screen. So go to
where are you sharing it?
I'm not sure. Maybe go to your full screen. 4 fingers, swipe to the left or right. You know how you can go between main full screens? It probably popped up as a full screen somewhere else.
Can you just send me the link again?
Yeah.
Thank you.
Right. There it is. Send that over for you. Are you typing the link in there? Oh.
No, I'm not.
Oh.
It's opening.
It's opening? Okay.
I think it will ever open. Just write and then I'll figure it out.
Yeah, why don't you try it yourself too? Because you're pretty much there.
What am I looking for? pH?
Yeah, you're looking for pH and the H2PO4 concentration, right? So now I'm working on the pH. So to find pH, you need to find the hydronium after the second dissociation, right? Which will just be 0.0461 plus the X. But you know
plus the X?
Yeah, plus the X, but that's not really going to make much of a difference. It's still going to be about 0.0461. Right, so then when we go...
But I thought I was finding the pH for H2PO4.
You're finding pH for H3PO4. What happens after it dissociated its proton twice? Can you share screen again? Share your thing. I want to see the answer on there.
How the heck am I supposed to share my screen?
Yeah, just go on Zoom.
Oh. But, okay.
Yeah, I stopped sharing mine, so you can share yours.
want to go back.
Oh,
okay.
you're not even on Zoom with me. Oh,
No, that's why I was confused. I was like, what FaceTime do you have?
Okay.
Ah!
Shoot.
How do I mute you? Oh, I just mute my computer, never mind. Okay. Share screen. See, it says H2PO4. No, it doesn't. Never mind. Yeah, are you sure it's not the pH for H2PO4?
Where did it say that?
I don't know. I'm just
Could you
like.
go up a bit?
Can you see that? Because at the end, you know where it says like what X is supposed to be?
Here, scroll back up a bit.
See it?
I think it's lagging.
Okay, great.
Alright, so we have...
Well, it says the pH is supposed to be 0.8. So what I did that.
Okay, negative log... and pH equals to 0.35 molar. Yeah, see, the question says find the concentration of H2PO4 and the pH of a 0.35 molar solution of H3PO4.
It says that. What does it say?
Yeah, and I think these solutions are actually wrong there. Can you verify with your teacher once? So calculate. So you should be able to calculate the pH at the end of it all, which you have right here, and also the H2PO4, but it's gonna be different from the values up there. And I kind of double checked it already, and I like our answers better. So why don't you check with the teacher and see if there's a wrong solution there, or maybe we just made a calculation error, in which case we'll probably catch it next time.
Okay. Wait, so I find the
H2PO4 minus is by plugging into this equation here, 0.0461 minus
and
X.
then do I add them together?
Well, you subtract it. Oh, no, you don't add it from together, because it's already been... You don't add it from that previous ice table.
Then
because
which one do I use for the pH?
At the very end. Right here, after second deprotonation. Because look, this, for example, look, you already added it because you already brought that value down here. Right? And then for the H3O plus, you already brought that value down here. You already brought that down here. So you've already considered that as the initial again.
So yeah, but what value am I using for pH?
This H3O plus at the end here. 0.0461 plus whatever X is.
So how do I know to use that or to use H2PO4?
You don't use H2PO4 to find pH, right? You use the hydronium concentration that it gives you.
Oh yeah. Never mind.
Yeah.
Okay.
Okay, so why don't we set up for next time, and then hopefully we can work a little bit more on this and also on buffer solution after you do a little bit of homework on this.
Bye.
Okay, I will see you later then.
Alright.
Okay,
Bye.
alright, bye. Alright, next lesson. Next lesson should be a grade 12 physics. Let me just send over. Yep, next one should be a grade 12 physics / calculus. So we should be getting some calculus problems coming in and grade 12 physics problems. Okay, let me open up the next board. Hey Varun, how's it going? Hey Varun, hey, how's it going? Alright, so we got this problem here. I got your email, so I'm guessing let's start off with those two questions you gave me. Okay. So the first one says a pair of parallel plates that are separated by 2 centimeters. Okay, so we can draw a parallel plates right here. So a set of parallel plates. They're separated by 2 centimeters. And I am assuming that this is the width they're talking about. It's the 5 centimeters across like this. Okay, a 420 volts potential, so V is going to be equals to 420 volts in here. So we'll see if we need to turn it into meters. So most likely we need to turn the centimeters into meters. Okay, so maintain, so the top plate is positive. So top plate is positive. So if I were to just draw one arrow indicating the electrical field, which way would it be? Which way would it be pointing? From the bottom plate towards the top plate, or from the top plate to the bottom plate? Top plate to the bottom plate, right? Because by definition, a force field is what happens if you put a positive test charge on there. What would happen? And if we do, it's going to repel away from the top plate, which are positive, and attract to the bottom plate, which is negative. So there you go. And now it says, okay, so I'm going to erase that because we can just know that in the back of our minds. All right, and I'm actually going to relabel this 2 at the end here. So I'm just going to write 2 centimeters like that. Okay, still separating the 2 plates. A single proton is fired into the apparatus from the bottom corner. Okay, bottom corner at 45 degrees. They didn't say left to right, but I'm just going to put left and from left to right from here. So this is going to be 45 degrees. And it's a proton. So you know what the proton is, the charge of the proton is. Charge of a proton is going to be positive. So P plus is going to be 1.6 times 10 to the negative 19. And this should be negative for electrons, so it should be positive for protons. So that's something we'll probably need. And oh, you actually have it written down up here as well. So that's the QP equals to 1.6 times 10 to the negative 19. And it also gives you mass because, you know, we're going to need mass to find out its accelerations. Okay, so we're not saying this is like top and bottom, so we can probably ignore the mg. We'll see about that in a second, because this doesn't really tell me that the negative is at the bottom, from the bottom corner. Maybe though, we'll see. What happens to the proton? Does it hit the top plate, or does it hit the bottom plate? If so, how far along, or does it escape? Because a couple of scenarios, right? You can either have it being pulled back by then and hit the negative plate, because, you know, the forces are basically going down this way, or you can have it being pulled not soon enough that it travels all the way out of the plate first, so that gives you the 5 centimeters right there. That's what that's for. Or the third option is it's not able to decelerate enough that it crash into the opposite plate first. All right, in that case, there's going to be another type of force that kind of applies to it, which is the normal force. I doubt that's going to happen. That's usually not that case. So you may assume there's a vacuum between the plates, such as the proton does not experience air friction, and yeah, we can see that gravity is insignificant. So if this, sometimes you have problems where, you know, this is up and this is down. So on top of that force of the electrical field, you also have Fg coming down. Although with such a small mass, it's probably not going to be that significant compared to that force of electrical field. Okay, anyways, we are ready for this now. First of all, let's draw some free body diagrams on this guy. If I draw a free body diagram on the proton, what do we have in here? Yeah, we have, well, free body diagram, we're drawing Fe, because force. We can figure out what that is. And that's pretty much it, right? That's the only force acting on it. That's the only force. So let's figure out what that force actually is. So how do we find a force given its electric field? Actually, we don't have an electric field yet. We have to calculate that. Given the voltage between the two, what's the electric field? You have your equation sheets in front of you? Okay, you should find those, because it should not be hard to find the equation that that you can calculate. KQ equals to what? Oh yeah, no, that's not the equation we want, and that's because look, yes, I know that Fe is equals to K, which is the constant, Q1 Q2 over R squared, right? This is not such a useful equation in here because actually, yeah, this is the equation you use, because, you know, and so how would you use that in this context? So you're missing, that's not the exact equation I want, but you can derive. Well, this whole thing is basically the electric field, right? KQ1 except, so ignoring the Q2. So this whole thing is E, electric field. So Fe essentially is the electric field times Q2. So if we have a way to finding electric field from your voltage, then we're good. Yeah, there's an equation that relates the voltage, the distance between the plates. I believe it should actually be area of the plates. Yeah, and also the electric field. So what is that equation there? So for voltage is equals to what? E over Q, exactly. So voltage equals to E over Q. All right, so a single find at bottom corner at, okay, 3, that's the speed there. Okay, what can we do here? So voltage times Q is going to give you the electric field pretty much. Let me pull out an equation sheet. Where's your equation sheet? Is it a physical copy or? Let me paste all the equations down so you can kind of pick and choose. I think it's E equals to V over D, no? Did you see something like that? Oh. Yeah, so electric field is going to be equals to V, which is the voltage, and the distance between them. Do you know what the units needs to be? So voltage needs to be in volts, and then distance needs to be in meters. Yeah, because technically this is not just voltage, but it's actually coulomb, joules per coulomb. So joules per coulomb. All right, so therefore the electric field here, E, I can calculate, and it's constant throughout. That's just the truth about a parallel plate. E is going to be equals to, in this case, 420 joules per coulomb divided by 2 centimeter is 0.02 meter. So 420 divided by 0.02, then we have 21,000, and what's electric field measured in? It will be Newton per coulomb. Got that? Okay, so Newton per coulomb. And then we can actually find the force now, right? Because we just said earlier, force is equals to electric field times Q2. So that means that Fe is going to be, so force being felt by this, what is this, an electron? Oh no, this is a proton. So felt by this proton is going to be equals to the electric field, 21,000 newtons for every coulomb times however much coulomb that actually is. So that's actually a 1.6 times 10 to the negative 19 coulomb. So let's multiply those. Then we have 3.36 times 10 to the negative 15. So once again, that's 3.36 times 10 to the negative 15. And that's a Newton. Okay, so we have our force now. So now now it's just a projectile problem. You can almost think about this as, this guy firing a rocket at a something meters per second, and instead of a gravity pulling down this rocket or whatever it's launching, now this time it's the electrical field that's providing that force, also electrical force. So here I have, what was the velocity? I think it was, yes, 37. So 3.7 times 10 to the 5, for example. To the 5, and then that's meters per second, and it's some kind of angle, 45 degrees. Okay, actually we can probably use a shortcut. If you can remember the shortcut, I'll let you use the shortcut for level launch. If you don't remember the shortcut, then just do it the full way. Okay. Yeah, because if you use the shortcut for the range, then you can see if that exceeds the 0.05 centimeters or not. Okay, but if you do it the proper way, it's not too hard either, because 45 degree, cos 45 and sine 45 are the same thing. So so I will do it the long way, and if you can do it the short way, you can do that. So Vx is going to be 3.7 times sine 45 or cos 45. So they're both going to be 261,629.5. Thanks. Oh, I just wrote AY is 9.81, but I know that's not true. It's actually 3.36 times 10 to the negative 15. Oh no, that's not even acceleration. Whoops, what am I saying? We need to calculate acceleration, right? That's F equals to ma. So it's actually the force divided by the mass first. And no need to change the unit there, because kilogram is what we actually want. Alright, so that's a much faster acceleration. And since we determined the direction of the electric field, we know that acceleration is going to be pointed downwards. Okay, how far along are you? Oh, so you gave up on the shortcut equation? Okay. Okay, so you can split them into x component, y component. Let's see what the question was actually saying. Does it hit the top plate? Or does it hit the bottom plate? Okay. So I guess we can find a it's like finding the height of that projectile, right? Let's check for that first thing. Does it hit the opposite plate? So let's check if the height is ever going to exceed the 2 centimeters. So again, I can split that into x direction and y direction. So for the y, we have the v1. V2 for the highest height is going to be 0, right? Acceleration minus 2.012 and 10 to the 12. And then we're getting a delta D here. We're just checking if this D is going to be less or greater than the 2 centimeters. If it's greater than, we're going to hit the opposite plate. If it's less than, we're not going to hit the opposite plate. Okay. So this equation I expect you to remember though. V2 squared equals to V1 squared plus 2AD. Okay, I'm getting some ridiculous answer right here. Let me check the units here. That's a meters per second, right? Yes, that was a meters per second. This is in meters per second. Alright, let me try that one again. Yeah. That's really high. I think we messed up a negative. So, oh, here's why. It's not a negative 12. That's why. It's a positive 12. But you gotta stop copying my numbers, bro. My numbers not right. Yeah, it's a 10 to the 12. Yeah, that's the issue. 629.5. I want to say I put that there to trick you, but I didn't. Just made a mistake there, so that's 12. Alright, that makes sense. So D is 0.017 meters, which means that's a 17 centimeters. Wait, no, 1.7 centimeters, which is good, as I predicted. Most of the time, this problem is not going to be interesting if you hit the opposite plate, because then you have to deal with impulses and all that. You know, you got to bounce back and yeah, so that's not what we're going to deal with in this level of this course. So now that we figure out it's not going to hit the parallel plate, well, let's see when is it going to come down then. So when is it going to come down? That's a whole separate calculation. So I'm going to set up X and Y again. This time, what I'm going to say is V1 is still the same as 261629.5. V2 though, I don't really need this time. Alright, but acceleration is still the same, negative 2.012 times 10 to the 12, not negative 12. This time, what can I say about the delta D though? If it lands back at the same spot in the Y direction, the delta D is pretty much 0, right? So this time, I need to solve for T. Because if I can find the T, I can transfer it over on the X side, the X component, because that is a constant velocity over on that side. On that side is constant velocity, which means we only have 3 quantity, V, D, and T, relating those in a constant velocity equation. So if we can find the T here, we can transfer that over onto the T for the X. since we also have the v1x, which is conveniently the same number as the y component, just because of that 45-degree angle. And now we can actually find the distance. Okay, so we're going to do that now. So hopefully you still know all your kinematic equations. And this is probably a quadratic one. Well, actually, no quadratic equation needed because we don't have a c term, right? We can just factor out the t from here. Or rather, even negative 1.006 t. Get t. Oh, I forgot the times 10 to the negative 12. Got a value for me for the time? Yeah, well, it's got to be plus. Your time's not going to be negative, right? If it's negative, you probably got to reject that one. So I have t equals to 0. I also have t equals to 2.6 times 10 to the negative 7. And you can consult my Zeitboard if that's not the same number you got. Yep, and that should be in seconds. So now we can transfer that onto my x direction. So this is pretty much projectile, except the beginning part where I forgot what the force actually was. Right, so then if v equals to d over t, then d must be equals to v times t. So we're just really multiplying those two numbers together. And we got 0.068 meters. And how wide was that thing? It was 5 centimeters. Yeah, so you can tell me if it's going to hit the plate or not then. Yeah, it's not going to hit the plate because, you know, we travel further than the 5 centimeter width, which means we're going to miss the plate. Is that the solution you got? Do you have a solution for that? Yeah, just check the solution, but I'm pretty sure the numbers look right. The steps definitely look right. Okay. Alright, then we go to your second question now. Oh, shortcut was, let's look that up because I don't remember the shortcut either. Level launch, projectile equation. So, you know, those pulley stuff, they're always a little, you know, if this condition is met, this condition is met, you know, we can find a shortcut equation, like for example, you know, the slant, you know, when you have something on a inclined plane, you know, g sine theta is the shortcut for the, yeah, so that's things like that I'm talking about. Yeah, so level launch short cut equation, and we can probably derive it, but I don't want to take the time to derive it right now. Shortcut, so I'll show you what that is and we'll use it together and just make sure we get the same number. All right, so they're saying the height of a level launch, so if you are launching at the same spot as you are, so nothing is raised over the other, you know what a level launch is. The h, so for level launch, the max height that it achieves can be given by v square sine square theta all over 2g, and then the range can be given as v squared sine 2 theta over g. So actually that's, yeah, we can get the solution right away if we plug these in instead then. So let's just try the height one. So for the height one, if we plug it in, oh, if this works. So this time when we use the v, we actually don't even use the component v, right? We use the actual v, which I believe it was what, 370,000 meters per second. So we're gonna square that. And then sine square theta, we're basically gonna take a sine 45 and then square that. Oh, turns out it's just 0.5. Okay, and then divided by 2. Oh, wait a second. Yeah, 2g. So instead of g, we're basically writing the acceleration. Yeah, because it used to be the g was the a, right? Now the a is going to be your negative 2.012. Okay, let's see if this gives us the exact same number. So we're expecting this to give us the answer of 1.7 or 0.017 first, and then we can convert it back to centimeters. So hopefully this works. Let me try as well. Yeah, and for A, we don't really have to care about the direction of it, because this is only going to give you a magnitude right here, right? Because we're kind of blending in all those angles and stuff in here. So we do see that we get 0.017, and that's in meters. So that's going to be 1.7 centimeter. And I believe that's what we got last time. Yeah, that's what we got. And then might as well, let's just cover the second one. So the second one, you're going to use the range equation. But I hope, just make sure with your teacher, she's actually okay with you using this, right? So sine 2 theta is going to be different. Sine 2 theta is actually a sine 90. So this time the 2 theta multiplied to the angle first. This is also divided by 2.012 times 10 to the 12. All right, let's try this one. Yeah, sine 90 you should already know, it's just 1. We've done that in math. 3.012. All right, and this one works out as well. 0.068, and that is equals to 6.8 centimeters. Yeah. So I would I'd say you should probably do it, like, know how to do it the first way. You know, the second way is just plugging in, so it's not, you don't even need to understand it, which could be problematic if they change up the things a little bit. Right. because they didn't have to enter from here. They could have, because most of the problem actually, this is actually a little more interesting, trying to make it into like a projectile. But I'll tell you, the classic problem goes like this. The classic problem tells you that you shoot horizontally right in the middle. And then they tell you, oh, is it going to make it out of this thing, or is it going to hit the middle? Kind of like projectile, right? But except this time it's not a level launch, so you can't use a level launch equation. And this time you actually have to separate the x and y component. Well, this time luckily the y component is zero. But this time you also need to consider the distances are a bit weird now, because this time you started off at a distance here. So for example, when I'm checking if it's going to hit the opposite side, this time if it exceeds 1 centimeter, then then it will hit, because it only takes 1 centimeter to hit to the opposite plate. You know what I'm saying here? Yeah, so just be careful. I'd say these are more popular than, but it is also easier in a way, because you don't have to break them into components and stuff. Okay, so I hope that answers the question number 1. And then now we are going to go look at question number 2. Let me just paste that over. Alright, so here is the question number 2. So it says here, hydrogen atom question, okay? The hydrogen atom to be a classic system. It's not, but never mind. Wait. Is that a grammar error? Okay, but doesn't matter. It says the hydrogen atom of a single stationary proton being orbited by a single electron at a distance of 53 picometer. Yeah, so picometer is, and I think, yeah, picometer is 10 to the negative 12, because it's one magnitude, well, 3 magnitudes lower than the nanometers. Alright, so they're saying a proton goes like this. So a hydrogen atom has a proton here, and it has a negative, so this is going with the Bohr-Rutherford model, right? So they're saying that orbit radius is going to be 53 times 10 to the negative 12 meters, because it's 53 picometer. If the electron is held in orbit by the electrical force alone, what would be the orbital frequency? Okay, so this is tying in with the centripetal forces stuff, right? So we know that centripetal force here, which is same thing as saying it's supplied by that electrical force. What is that equals to relative, the v square and all that? Yeah, I think it's like mv square over r, right? Yeah, okay. My pen is lagging a little bit today, so just give me some time for this word to show up. Alright, yeah, that's not what I wanted. Okay, so we have m v square over r. I'm not saying we're needing it right away, but if they want frequency, we should probably go for another shortcut. There should be on your equation that relates frequency instead. Is there one? Centripetal force and frequency. Yeah, there should be one that relates to frequency directly. You can probably find velocity first and then get to frequency, but alright, because if you can find a tangential velocity, you can figure out how big the circle of this radius is by doing pi r squared, and then you can probably, but if we have a shortcut, and this shortcut equation is always going to work for this kind of problem. Okay, if you can't find that, then I am going to have to. Okay, then don't worry about it. Then we won't do the shortcut. We're going to do it slowly, one by one. So we're going to say the force. So if we can figure out what the force is, we can probably get to the V, because we have the mass, we have the radius, correct? and then the mass is relative to that electron, and then the radius, we have that. So let's figure out first of all then what is actual Fe then. What is the force of the electrical attraction? Okay, so this time we can actually use that equation we said earlier. Fe equals to Q1 Q2 times K over R squared. Yep, so you're gonna go ahead and do that for me. So we have Q1 Q2. What's the K constant again? 10 to the negative 11? Negative 9, okay. Oh, 9 times 10 to the 9. Right. Divided by the radius squared. So radius squared. Alright, so we have a force of attraction there. Let's just take a little more decimals. You're doing this as well, right? Okay. Okay, so let me know once you get that force. Oh, you're solving for V now? But just before you do that, am I using the mass of the electron or am I using the mass of the proton? Electron, right, because it's relative to the tangential velocity of the actual electron. So we're going to use the electron because, you know, just because the charge is the same doesn't mean the mass is the same between proton and electron. In fact, the electron is quite a bit lighter. You want to verify the velocity with me because I'm not. I feel like I did some calculator mistake. Okay, I'm gonna go calculate that one more time. Okay, so even if you forgot to square root that, that's not just the only problem then. So I probably either made a mistake or you made a mistake because you didn't square root it yet, right? Oh, you did square root it. What did you get? 2.1 times 10 to the what? Okay. Why are we there? I got 2.184 times 10 to the 6 though. Okay, how did you do that? So I started with 8.202 times 10 to the negative 8. Multiplied that by 53 times 10 to the negative 12. And then divided by 9.11 e negative 31. Yeah, that gives me 4.77, and then I square root the number. So square root the number should give you positive, like how can 10 to the 12, if you square root that, it should be 10 to the 6, right? Yeah, maybe square root and then answer, so you're not. What? Now you're getting different number every time. Oh, before you square root it. 8.202, okay, e negative 8 times 53 e negative 12. I'm getting oh yeah, that's a negative, because that's the mass of the proton. Yeah, mass of electron can't be that big. Okay. All right. Then what do we do? We're nowhere done yet, because now we have the velocity. So that's the tangential velocity. I don't care if it goes clockwise or counterclockwise. But think about what frequency is. Frequency, first of all, is the inverse of period, right? Frequency is 1 over the period. If we can find the period, we can find the frequency. Right? So it depends on which one you're more comfortable with. I like period better, just because, you know, I tutor a little more math than I do physics. And in math, period, I know it's the amount of time, or the amount of x-axis that goes for one cycle. So this is just basically saying how long it takes for you to complete a whole circle. So how do you calculate that? So to calculate how long it takes for a whole circle, well, you're going to basically say how long it takes for a full circle. That's the time required for that whole thing. So time, so v is equals to distance over time, right? So basically we're trying to solve for time here, where the distance is the full circle. So let me just rearrange that. T is basically going to be the distance of the whole circle. Yeah. Yeah. That's what I'm saying. That's the shortcut equation I was saying earlier, yeah. But I'm trying to reason to you where that came from, right? That's pretty much putting a combination of a few. Yes. So if you know the shortcut equation, we can use the shortcut equation, right? So it'll be m times 4 pi square r over t square. There should be another version with just f, right? Or you can just punch in, right, t over f. Yeah, so basically that's what you can do that right away. But I'm gonna continue here. I'm just gonna continue you can use the shortcut if you like. But if I continue on here, I'm just reasoning in case I forget the shortcut equation. This is where that came from. We're saying a period is how long it takes to travel a full circle. Well, that's going to be equals to the length of the circle, which is going to be 2 pi r, and we do have the r. R is just the distance, the 53 times 10 to the negative 12 meters, divided by my tangential velocity, which I just got earlier, equals to v. So if F is equals to that, then I mean F is just going to be the inverse of that. It's just going to be V over 2 pi r then. So it's just really 184 times 10 to the 6 divided by 2 pi times the radius. And you can tell me if that's the same number you get from the shortcut equation. Divided by 2, divided by 3.14. So I'm getting frequency of, and as expected, it would be quite big because these electrons are traveling quite fast. 6.56 times 10 to the 15 meters per second is what I got. I think you had a solution attached to there. 6.56 times 10 to the 15, yeah. And that's per second, which is hertz. So, yeah, sorry, I wrote meters per second. That's supposed to be per second, because it's measured in cycles per second, aka hertz. Does that make sense? Should we use the shortcut equation one time as well? But I think that one's just plug. Yeah, if you solved it using the shortcut. And okay, take your time. Okay. All right. Do you have another problem? Okay. Let's see. When do you have a test on this? Oh, right. So do you even have any more tests for the rest of the year? Okay. So this is more of learning for next year, I guess. Like, do they give you like a formative test or anything? They send you like a. Oh, okay. And for math, do you have no math questions? What's going on in math? Yeah, can you remind me what we did last week? It was. Let me go. Oh, right. You did some. Let's see, how far into log are you? Maybe we'll do some of those because we don't have too much time. So maybe not a full physics problem. Oh, you were doing the exponential decay and the. Okay. Have you got into the log rules yet? Maybe I can get into the log stuff with you now. Okay. So some log rules are like this. So this sometimes you're gonna get into a log chapter, and this is another part that kind of confuses people a lot in advanced function this year, because a lot of students never really touched the log before. All right. So you first of all, you should know how to rewrite this as an exponential form. So if I write log base x of a is equals to y, maybe I should actually use base a instead. Log base a of x is equals to 4. Can you rewrite this equation in terms of exponential form? Yeah, exponential log Logarithmic. Logarithm rules. Sorry, what is it? What is the yeah, a to the power of y is equals to x, right? So that means when you find log base 10, for example, log base 10 of 100, that's basically saying 10 to the power of what gives me 100, and you know that's got to be 2. Yeah, so you know that. You know your exponential rules, so this is definitely one thing you need to be able to do. Go back and forth between the log form and the exponential form. Second thing, you need to know the parallel between the exponential rules and the log rules. So check this out. When you have x to the power of a times x to the power of b, you must know this already. It's adding them together, right? And log, that is going to have its own equivalency. So imagine if I log both sides here. If I log both sides, I get log. Actually, you know what? I'll just give you a totally different set. So log base of something, x times b right now. Okay, so if I have x times b, that's same thing as saying log base b. Oh, you know these rules already? Have you done a lot of exercise with them? Maybe I'll just give you. Oh, really? So why are you backtracking to exponentials then? Oh, okay. I guess they're going out of order a little bit. Okay, why don't I just give you one problem and then if you can solve that, then I'll just let you be for now. So for example, can you simplify this for me? So 3 plus 2 log base 3 x plus 5 log base 3 y. I want you to express this in a single logarithm. So as a single log, I want you to write it. Alright, so for you to combine them together, you probably need to use that rule I just mentioned. So you probably want to express them in terms of the same log base. Okay? Wait, say that one more time. Oh yeah, okay. Log 3, well, there's no equal sign here, right? You're not bringing anything. There is no equal sign here. This is just simplifying this expression. So you want to rephrase that? Log 3 10 log 3 plus 3. X plus y. Okay, so I'll tell you what went wrong here. Wait, you saying xy or x plus y? Xy, right? Okay. So the problem right now that you did is you try to multiply the 2 and the 5. And I'm not sure why you went and multiplied that. So you must have got that 10 for multiplying the 2 and the 5. Okay, so there's no rule says that you multiply. If for example, this is 2 log base 3x and this is 5 log base 3x also, that you can add them, but even if you add, you're not multiplying. So you're never really gonna find a situation you're multiplying the 2 and the 5, because in this case it'll be 7 log base 3x. But the problem is this is a y, so they're not even the same, so they're not even like terms. I cannot combine those coefficients. Your first move should actually be bringing the 2 up there. So this becomes 3. This should actually be log base 3x squared, because I can't even go and try to combine them back into this way unless I don't have any coefficients in front of them. If I have coefficient in front of them, you can't say that. You have to bring it back up first. So I bring it up there. This one also, I bring it up there. I get y to the power 5. Now I can combine them. But let's go one step further. Why not include the 3 in there? Because 3 is almost like saying 3 times 1, right? So if I rewrite 3 as 3 times 1, perhaps then you can write 1 better. Because 1 is just log base 3 of 3. So in this case, we can do the same thing. We can actually bring the 3 up. Bring the 3 up. Okay, I'll just write one more line. I will not be lazy. If my pen wants to work. Actually, you know what? Sorry, we're out of time a little bit, so I will be lazy. So 3 to the power of 3 is going to give you 27. Don't tell me 9. So it's 27 here. So now we can combine all of them together. Because now we can say, well, the rule is if you add them all of these log with the same basis with no coefficients in front of them, all we got to do is just multiply whatever is in each of those logs. So it's going to be 27 times x squared times y to the 5. And then there you go. That's my final answer. Okay? I know this is probably not part of what you need to work on, but you know, if you're in the log chapter, you should always know your log rules and exponential rules well. So I guess I will see you the same time next week. Work? Okay, I'll see you same time next week then. Okay, see ya. Bye.